Hello. I'll go with the NEORV32 plus NPU plus camera controller system features. This video is not a setup guide. The setting up the project is covered in another set of videos. So this is the actual NEORV32 top level file. Here we pass the ECP5 peripherals and onboard physical pins to the NEORV32 and associated peripherals. So we'll start with the cameras. ECP5 clock. So ECP5 has three onboard clocks. One is the 12 megahertz oscillator. There is an unpopulated spot for a 50 megahertz oscillator, and then there is a 200 megahertz oscillator, but that is only available for SerDes applications. So we are forced to use the 12 megahertz clock. We also pass the reset push button pin from the from the ECP5 board to reset the NEORV32 plus associated systems. If you want to see any activity output or anything, LED pins from the ECP5 board can be passed or can be used. We pass two pins from the ECP5 for UART communication. So this is used by the NEORV32 to, for example, you send and receive data from GTK tone. Lastly, here's the camera interface. So the SIOC and SIOD pins are the SCCB pins, just similar to I2C, and are used to program the camera's onboard registers. We have the VSync and HREF signals. So VSync starts signals the start of a new image frame, while HREF signals the start of a new row of image data. Pixel clock is a clock output from the camera itself. This is used to coordinate. It's sort of a handshake protocol. It is used to coordinate image capture between the camera controller and the camera itself. So when it's high, it signals that okay, there is like valid image data on the bus. Yeah. External clock. So the camera requires 24 megahertz 24 megahertz external clock to operate. This is generated by the ECP5 FPGA and passed to the camera controller. And data is so the camera OV5640 uses DVP or parallel video port to send over image data. So it's like 8 bits of data is passed parallelly to the system. So it's actually passed to the ECP5, which then passes it down to the camera controller. And we have the OV5640 reset and power down pins, which are used to handle the camera power up sequence, boot up sequence. So yeah, 12 megahertz is slow for our system, so we use a PLL block. So we use 12 megahertz acts as the input to the PLL block, and 72 megahertz is used as the system clock, while 24 megahertz is used to generate the XCLK or the external clock for the camera. OV5640 camera, as you can see. So ECP5 pins, in our case, we are passing it to the NEORV32 as GPIO output pins. You can use it for other things, such as for seeing activity on the camera data pins. It's for debugging. It's for showing that the system can work in a headless manner. You can use it in any way you want. Now here is the NEORV32 top level entity instantiation. So we modify a few of the generic parameters. So we pass the system clock as 72 megahertz. We increase the instruction memory and data memory sizes to 128 kilobytes, and we pass increase the set the number of output GPIO and input and output GPIO pairs to 8. Now the interesting, of course, so we pass the UART pins from the from the ECP5 physical pins to the NEORV32 for communication, the LED pins to the GPIO of the NEORV32, and this is the interesting thing. So we can't directly pass the camera interface physical pins to the camera controller, because the camera controller is a part of the NEORV32. It's instantiated under the NEORV32. So we need to pass the physical pins from the ECP5 board to the NEORV32, which then passes it to the camera controller. So here's the camera interface. Right. So here's the NEORV32 top level file. As we just discussed, we change the clock frequency, the instructions memory size, and data memory size, and of course the number of GPIO pins as well. You can see we modified the top level like port specifications to include the camera interface, like here. So the first, so these are components you can use component declaration or you can just do entity instantiation. Either approach is fine. So here is the NEORV32 top level instantiation, which is under here. So this is the top level file under NEORV32 top unit. So we pass in the values from the generic values are untouched. The important values that are modified is that of course we enable XBus, which is the wishbone bus on the NEORV32, and we pass in the system clock, the reset physical button pin from the ECP5 board to the NEORV32. The output pins, input pins are tied to 0. We are not giving the NEORV32 any specific input, physical input. We pass the UART interface pins from the ECP5 physical pins, and these are the XBus pins used internally. So the NEORV32 wishbone or wishbone in general, you can only connect one device at a time if that device only has one wishbone bus. So we use an interconnect, which is which allows us to connect two slave peripherals to one master, which is in our case is the NEORV32. So we pass the NEORV32's XBus pins to the wishbone interconnect input. So this is like the master port on the interconnect, and then we pass the slave peripheral pins to the NPU and the camera controller instances. Camera controller is find the so these are just simple instantiations. Nothing's been modified by generic map. This is, as you can see, just to show it can be done. But yeah, please note for the camera controller that this is like how we pass the physical pins from the ECP5 board to the camera controller, which is instantiated under the NEORV32. So first is the interconnect peripheral. As you can see, this is the slave 0 and slave 1 base address starts. So in our case, it's 9000 underscore xxxx hexadecimal and 9001 underscore xxxx are used as the base addresses for our slave peripherals. You can modify this via generic map. For example, how we did it for the NEORV32 IMM and DMEM generic map. You can do the same for the interconnect when you instantiate it in the NEORV32 top level file. Oh no, not this one. Yeah. So you can do generic map here and say, okay, no, I want to use a different set of base addresses for my peripherals and therefore require different mask as well. You can change it, for example, to 8000 xxxx, however you want to use it. The interconnect automatically handles communication. Depending on what data comes in or what address data comes in, the NEORV32 will select the appropriate peripheral automatically. Only thing to look out for is that the address maps do not overlap at all. Otherwise, there'll be you'll produce unexpected behavior, which you of course do not want for the system to work correctly. Now here is the NPU peripheral again. Here is the base address, the input tensor base address, weight tensor base address, bias tensor weight address, base address, and the result tensor base address. And similarly, all the control registers and setting registers used to set up the NPU for the convolution layer, dense layer, activation, pooling layer, everything can be set up. And these registers are, of course, the addresses of these registers are like generic values, so you can reprogram them as, change them as you want when you instantiate the peripheral in the NEORV32. So yeah, for example, it can be 8000 xxxx again. So yeah, this is so the important thing that we'd like to focus for setting up the NPU is the tensor operations base package, which is used by the NPU. Now this package is where we define the sizes of the input, weight, bias, and result tensors. So we use a word logic. So one word is 32 bits or 4 bytes. So when we say tensor A words 2500, it actually means that there are 10,000 bytes or 10,000 kilobytes available for tensor A. Now 36 kilobytes for the weight tensor, etc. Now these values can be changed depending on the size on the embedded VRAM blocks available on your FPGA board. So they can be increased, decreased, etc. All you need to know is that these are BRAM so the NPU automatically handles VRAM inference. You need not do like, you just need to change these values for using this system. Right. Next is the camera controller. So camera controller, again, the addresses and setting registers are like addresses yes, are part of the generic block. So you can change them to whatever values you want. So 9001 for example can become 8001 xxxx, etc. Now, as an important parameter here is the system clock speed. So here it's the default is 72 megahertz. Now you need to, if you are using a different clock speed, then you need to change this value as well. Now this is done for two important reasons. One is that the camera register is programmed via SCCB, which is a simpler version of I2C. It's like a less stricter version. And so the I2C SCCB bus uses 400 kilohertz. So we need to know the input. So, and we are generating this 400 kilohertz from the 72 megahertz clock speed value. So it it counts how many cycles have passed in 72 megahertz to generate one 400 kilohertz pulse. And so changing this value is essential if we want the system to work as expected. Similarly, for the camera boot up sequence, there are multiple stages where we would for 5 milliseconds, 1 millisecond, or 50 milliseconds, and the cycles passed are again calculated using the system clock speed. So the number of cycles for 60 megahertz and 72 megahertz will be different. So yeah. Lastly, here is the camera interface pins that we pass from the physical, these are the physical pins from the ECP file, top level file. Now, similar to the NPU, we again have a package file which defines the buffer, image buffer for the OV5640 camera controller. The important is the tensor words, again, which is 2500 words or 10 kilobytes. So we can store 100 by 100, the largest image we can store is 100 by 100 grayscale, which is like, in which each pixel is about 8 bits. So you can change this value depending on your, of course, VRAM block availability, or depending on your application. For example, if we didn't have the NPU, then we could have changed this value to be much larger. For example, we could have captured 200 by 200 grayscale images, etc. So you can change. The max dimension by default is 50 for synthesis purposes, but that can be changed for via the image resolution address, and we change it to 100 by 100 in application code. See this. Lastly, we have the constraints file. Now the thing to look out for in the constraints file is that we use the same voltage bank. So since the camera in our case used a 3.3 volt logic, we decided to stick with the 3.3 volt pin bank on the FPGA board. But for many FPGAs support multiple voltages. So in our case, the ECP5 evaluation board had one 3.3 voltage logic bank and one 2.5 volt logic bank. You cannot mix the two. For example, for my SCCB pins SIOC and SIOD, I can't put one in the 3.3 volt bank and one in the 2.5 volt bank. The system will not work as expected, and sometimes even the synthesis tool will throw unexpected errors. And talking about synthesis tools, the last point to remember is that you must use Simplify Pro, not the lattice synthesis engine. The system won't work otherwise. Right. Thank you.